All right, we are going to knock out part 2 of the mechanical advantage series here. So last time we went through kind of the capstan equation, but last time we really focused on counting tensions, which is very linear in nature that we talked about. So if you haven't done the counting tensions, then you may want to do that prior to this one if you're not really solid on that. But you're going to kind of start titrating into some nonlinear stuff on this, to getting into how we can exploit certain things and mess around with what our mechanical advantages really are. So we'll hit this up. Quick overview. We counted tensions to determine the theoretical MA. It was theoretical because we ignored friction, right? So in a perfect world, our pulleys would be 100% efficient. We'd never have friction over any surfaces, things like that. So when we count tensions, one comes in, one comes out. So we're losing nothing to friction, nothing to heat, and everything kind of evens out, and it's pretty nice. When we start adding some reality into things, we're going to start looking at the friction that is organic to internal of our system, which is our pulleys. So like we said before, if you're not solid on counting tensions, you may want to do that. Prior to, you can go back to YouTube or on our website and look at the counting tensions presentation. We're not going to estimate what the mechanical advantage is when friction is appreciated just into the pulley. So like we said before, there is no 100% efficient pulley. Each pulley, depending on how it's made, has a different efficiency to it. So we'll kind of go over that when we look at a couple of these pictures. So big important thing, remember, we're still not taking into account all the other areas that could affect what your mechanical advantage really is. So theoretical, we're getting into starting to add some things that'll tell us what our actual mechanical advantage is, yet we'll probably never really know that unless we try and assess what it is after we build the system. It's going over the windowsills or the parapets and all that kind of crap. But for our purposes, this will at least get us in the ballpark, and it'll start giving you an idea of the gear that you want to take with you. And even if you're trying to stay light and fast, what is that critical gear and where does it go within your system? So like we said before, we're not taking into account of friction gained over edges, windowsills, parapets, ice axe heads, different soils, other system contact areas. Even rope manufacturing varies on how efficient some of your things are within a pulley, depending on the bending rigidity of your rope, the manufacturing style that was taken into account, even getting into single versus double bobbin sheaths that are on there, and the stiffness of that. The capstan equation screencast that we did goes into a little bit of that, so you can kind of get a little bit better idea. So this is still inputting all the real world friction variables, which can be very significant and not always that obvious, but this is the first step to begin titrating reality into your system design, mechanics, and understanding the behavior of your mechanical advantage system. So for your essay, this is kind of what we got that we need to be cognizant about, is we are estimating the following efficiency values. This is what we're going off of for most of the slides that we have in here, except where something else is denoted. So on a high efficiency pulley, that is one with sealed bearings, we're looking at about a 90%, roughly plus or minus 90%. Understand, when you see an efficiency in a pulley, when it's advertised as a 92%, 93%, 89% efficient pulley, that is taking into account where all those pulleys measure efficiency on a steel cord. And that is just so they have an even playing field across for efficiency. When you get in there, there's certain diameters of rope, certain rope manufacturing techniques that can change that plus or minus. So you never really know it until you actually assess it in your own system with the rope you're using. And even whether that rope is more worn or it's brand new is going to affect that slightly. So for us, we're just going to say that high efficiency pulley, sealed bearing pulleys versus like a bushing. So anybody that goes back to their technical rescue barn or shed or whatever and has like bushings, those are usually around 70–72%. So the sealed bearings, much more efficient at 90%. If we aren't using a pulley and all we have is a carabiner, where normally a pulley would go, we're counting that at about right around a 45% efficiency for a gree-gree, just because we see that quite a bit. And we'll kind of get into that when we get to that slide. that's going to be estimated at around 28% efficiency. One note that we want to make too is we also looked at the EXO. Just because that's part of a bailout system and the way that it's advertised, you can make a 3-to-1, and we'll talk about that. That is actually less than what the Grigri is. On the EXO, we're looking somewhere around probably 23 to 25%, depending on the rope that you're using. And we'll kind of get into different ways in which that's appreciated in our system. Real quick note too on the Grigri, when we have an inefficient progressive capture in there, like a Grigri, as the mechanical advantage, if I have highly efficient pulleys in my system, and let's say I have a 3-to-1, that Grigri is going to be a little bit more efficient than 20%. If I make that into, let's say, a 5-to-1 or a 5-to-1 complex, 5-to-1 simple, and all those pulleys are efficient, that will increase that efficiency that's seen on the craptastic number that we have there when it's just in a 1-to-1. So when we look at those numbers on the right-hand side of the screen, those were appreciated doing a 1-to-1 pull test with dynamometers. And so that's basically putting 200 pounds on one side, and how much force is it taking us to lift that up? And that's where that friction is appreciated with that. But as we build a system, you can start gaining a little bit more efficiency as long as you're using efficient pulleys in your system. So that being said, following pages, we actually rounded up to at least the 100 spot. It can get a little goofy doing what we're doing, and it will wear you down mentally and physically. So I've got a calculator out here. We'll run through this first set, and then from there on out, we'll have those numbers, and we can kind of talk about that a little bit. So estimating efficiency. What we're looking at here is we're comparing the 3-to-1 Z-drag system. On the left is the system with high efficient pulleys, and on the right, we actually kind of substitute that for kind of that fast and light. We'll get into that a little bit more on the next slide. Of this is what I got, I'm building it, and it looks like a 3-to-1. So when we're counting tensions like we were in the last one, regardless of this, each one of these would come out as a 3-to-1. So if somebody's trying to sell you something and be like, hey, listen, man, you can do a 3-to-1, you can do a 5-to-1, you can build that all day, man. So when we were counting tensions, you know, one comes in, one comes out, one comes in, one comes out, one comes down and meets the 2. That's a 3-to-1. See, you can make a 3-to-1 out of this until you start looking at the efficiencies. And then that's where things start getting a little screwed up, where you start getting really pissed off at whoever sold you a system and said that you're going to be good to go on mechanical advantages with it, even though it's a bailout system. So just like when we were counting tensions, we are going to, and bring the calculator over here, we are going to start with a 1, right? That 1 is whatever your input is. So if we're looking at a 3-to-1, a 5-to-1, 6-to-1, 7, whatever you're looking at. That 1 is how much force you're putting on your hull line. And then from there, it gets, you're going to see that it goes through a process depending on the efficiency of what we're going through, where it takes that away because of friction. And we'll kind of get into that a little bit more. So as we're looking here, we kind of got some notes over here that I'll keep open to it. So we are estimated the high efficiency pulleys at 90%. So that means as we pull through with that 1 that gets carried down, as it goes in and out of that, no longer is it 1 in, 1 out. We're going to have to put that 1, and it's going to go through a 90% efficiency pulley. So as we start with our 1 over here, we can see 1 comes from our hull line. So that's whatever amount of force we're putting into the system. As that 1 travels down, 1 comes in, 1 has to come out, right? But kind of. So what we're going to look at is when 1 comes in, it's going to go through, and we're going to times that times 0.9 for a 90% efficiency pulley. And as that comes out, that's what we get, 0.9. So as 0.9 comes out, people will ask, well, what about, you know, simple laws, linear laws of physics with Newton and things like that? You know, energy isn't ever really lost, right? It transforms. So as it transforms, the byproduct of friction is heat. So when 1 comes in, it's not that that 1 is just evaporates and is gone. It transforms to heat, and I don't want to get uber geek on this. So that other 10% basically gets converted to heat, and it's dissipated into the air. So the energy is not necessarily lost. The energy is just transformed into something else. So what we see as far as our force goes, though, 1 comes in, 0.9 comes out. So if you think about your descent device after a long rappel, right, you go to grab it, super ass hot. That is basically what all that energy that kept you going from 9.8 meters per second squared and cratering into the ground. is converted to heat. Some of that heat is dissipated, some of that heat dissipated across your rope, on your device, and into the air. So as we go in, 1 comes in, 0.9 comes out because it's a 90% efficiency pulley. As that 9 travels back up through our system, it's going to go in and out of a progressive capture. If 9 comes in, 0.81 comes out. So if we're following this and you're following along with the calculator on your phone or anything like that, you're trying to figure this out at work, as that 0.9 comes in, all we're going to do is times that by 0.9 because we have a 90% efficiency pulley, and we get 0.81. Now back here on that first pulley on our Z-drag, remember if 1 comes out, right, 0.9, and 1 comes in, 0.9 comes out, we have to basically add those numbers together, and that is what's being held on our pressing. When we're counting tensions, it was 1 comes in, 1 comes out, and we have 2. Not the case when we're counting efficiencies. So 1 comes in, 0.9 comes out, 1 plus 0.9 equals 1.9, and that's what's sitting here on your pressing, and that's what's going to be added to this number. So as 0.9 comes in, 0.81 comes out, 0.81 travels down, it meets up with the rope grab. So regardless of whether this is a rope man, a T-block, a pressing, that is holding that 1.9 tensions and force in your line. So whenever you see that in a position where you have a pressing, that's going to be a plus sign. So now as 8.81 travels down, we add that to the 1.9 that's already sitting in there with the force, and then we have a 2.7. So when we're looking at this, now we can see that instead of a 3-to-1, we basically have a 2.71. This is in that situation where you're in an elevator shaft. You have no other tension, right? So that's what we were trying to really focus on is this is just the friction of the pulleys. So if you're looking at it, you want to optimize your system as much as you can, knowing that you're probably going to have other friction points with edges and things like that you're going to have to mitigate in real world. So that's what we're looking at. So really, in a most efficient system that we can look at with high efficient pulleys, your 3-to-1 actually is approximately a 2.7-to-1 before any other environmental pathology gets involved with it. So let's look over here to what we see quite a bit with folks that have bought systems, whether it's an EXO or whatever, that has an integrated device that is a descent control device. In this case, a Grigri 2, which is technically an assisted belay device. But we see these used as progressive captures all the time because a lot of people are like, hey, it makes it so easy. So if I have this as my progressive capture and I'm hauling, I jam up that load, I've got to release a little bit. It's really easy because then I can just put, just basically go into a brake position, use the lever on that Grigri and be able to lower that, which is an advantage if you weigh everything out at times. There's way easier ways to do that with VT process and things like that, that you don't have to mess with that and lose as much efficiency as you are. But let's take a look at that same 3-to-1, right? This is going to be a 3-to-1 if we count tensions. But if we count efficiencies, we're going to be completely disappointed, right? So that 1 tension comes in, and because you're light and fast, right? You know, you don't need a pulley here. You just need a carabiner. I'm saying that obviously very sarcastically. And so when 1 comes out, we're going to times that by the friction that we estimated with our carabiner, which is about 45% efficient compared to the 90% efficiency of this sealed bearing pulley. So 1 times 0.45. And now we start the process. So 1 comes in, 0.45 comes out. So because 1 came in and 0.45 came out, we add those together, and that's what's sitting right here on our pressing. 0.45 comes up towards our progressive capture. Now, our progressive capture, we're estimating to be approximately 28% efficient. So that 0.45 now gets times by 0.28, which is the 28% efficiency that we have in the Grigri 2, which equals 0.126. So you can see our force is getting treated like it was in prison, right? So now that 0.126 rolls down here, meets up with the rope grab. That's a plus sign. So now 0.126 plus 1.45 gives us approximately 1.58. We can round that up to 1.6. So when we're looking at that system, same exact system, we just had efficient pulleys in here. It's night and day, right? So we have a 2.7-to-1 mechanical advantage here on the left. On our right, it's approximately about a 1.6, 1.58-to-1 mechanical advantage. So when you're looking at this and you're trying to figure out, you know, hey, the vendor told me this thing, I can build a 3-to-1 off of it. Remember, if you're talking about a bailout system or anything other than something that has a moving wheel in it, like a pulley, that device was meant to keep you from cratering into the ground. So it is organically made just to produce a lot of friction to keep you from killing yourself, going over edges. So when you're using a descent device or ATC or anything like that that's meant to have enough friction that it keeps you from falling if you're rappelling with it, know that it is not going to be awesome in a mechanical advantage at all. So this is one thing. So, you know, when we talk about a 2.7 to 1 versus a 1.6 to 1, to put it in the context a little bit, what we'll do is we'll say that we know the weight of the load, and then we'll work it out there and see what those differences look like. So our known on this, to see how much we have to input into that haul line to actually get that thing moving, we will assume that we know the load weight, which we're going to say is 200 pounds. So we set up a 3 to 1 to be able to haul up 200 pounds. So knowing that, we can take those numbers we just did, which is 2.7 and basically 1.58, and we will divide that out of 200. So as you can see here, in an efficient system with efficient pulleys, to move 200 pounds, I will have to input approximately 73.8 pounds to get that moving. So whether that's me pulling myself, or I've got a couple guys that are hauling with me, that input force needs to be approximately 73.8 pounds. And you can see as that moves through how that works. Same thing, 73.80. And I'll bring the calculator over here just so you can kind of see that and for these first couple. So we estimate that, as we said before, just to start from the beginning, we take 200, we divide that out by what our estimated MA is going to be once we count efficiencies, which is 2.7. And from there, we get our 74 pounds. So when we did that without guesstimating up, we went ahead and said, okay, so we're at 73.8 pounds. As 73.8 pounds goes in, we times that by 0.9, and we get 66.42 out. As 66 moves up, right, we times that by 0.9 to see what we lose. So as 66 moves up, 59.78 comes out. As 59.78 comes down, it meets up with our 140, 140.22, which is what 73.8 and adding that to 66.42 equals is 140.22. So we add that 59.78 to the 140, and we get right around 200 pounds. And so that is what that weight distribution will be based on the efficiency of that exact system, minus any edges or anything. Compare that to the 1.6 that we have over here. So if we take our 200 pounds, divide that out by our 1.58, we're basically coming into saying, okay, we're going to have about 126.6 pounds that we're going to have to input compared to the 73.80 over here. So when we're looking at that, that is a pretty large difference. And then obviously you can see how the weight gets distributed through there. I don't really care a whole bunch about the weight distribution as much as soon as I figure that out, I just times it by what my estimated weight is to see how bad it's going to suck. How many extra haulers we're going to have to put on that line versus me being able just to haul it myself if I'm using highly efficient gear. So that's kind of putting in perspective. You can kind of test those systems out by what you estimate your estimated load going to be, whether it's a 1-person rescue, a 2-person rescue, what that estimated weight is going to be, and then times it by what the estimated efficiency is of your system to see if you're kind of in the ballpark of where you want to be. And that about covers that for this slide. So big deal. When we look at it, we notice on this last one, if we are one of those groups that got sold, let's say an EXO, and we believe that it's going to be a 3 to 1, man, I can do a 3 to 1, 5 to 1 with that. That's all I need. So now with this great ass kit, I'm going to be able to freaking rescue the world and also bail out and all this other crap. But kind of, right? So we can build it and it looks like a 3 to 1, throwing a T-block on there and not using pulleys because you're light and fast, because you're super tactical. And then let's just really see what happens to that. So this is the system we just went over, right? Which was on the previous page where 1 comes in, 0.45 comes out. We get an estimated value of 0.6. It works out to 1.58. So we're pulling on that thing. And let's say we got a pretty good load. Let's say we're trying to work a 2-person load. We got enough haulers. And it's still, we're on the struggle bus on this thing. So if this is our light and fast kit, right? We're probably not carrying pulleys. We obviously have a very low efficiency PCD, a progressive capture device. And that 3 to 1, which is actually working out to be about a 1.6 to 1 MA on the left, isn't cutting it. So we decide, because we're voodoo, that we're just going to grab another rope grab, and we're going to attach our other carabiner and make a 5-to-1 complex. And what we're going to do, right, just to make a 5-to-1 like we did, is, so here's my 3-to-1. All I'm going to do is throw a rope grab on here, regardless whether it's a rope man, T-block, or prusik. I put my extra carabiner on there that I have set up for that 5-to-1, and using no pulleys, I throw my rope through that thing. Now what we see is just terribleness, man, just awfulness. So as one comes in, 0.45 comes out. As 0.45 comes out, we times that by a 45 efficient pulley, 0.20 comes out, meets up with my 1.45. And in this section, going into my very inefficient progressive capture, I have 1.65. 1.65 comes in, we times that by 0.28, and we have 0.46 coming out. That 0.46 runs down here. We have an addition sign here because I have a rope grab that's holding 0.65. So in the end, what's crazy is I have nothing efficient in my system. So once you go beyond a 3-to-1 on your highly inefficient bailout system, you actually lose mechanical advantage the higher you go. So our 5-to-1 is actually works out to be about a 1-to-1. So it would be better for you at this point to just take that shit off and just pull on your basically just on your 3-to-1. This is about as efficient as you leaning over the edge and pulling them straight up on the rope without using any hardware whatsoever. Not good. So what you did is you reached a tipping point of friction. So you brought inefficiency in. That inefficiency comes out. So garbage in, garbage out. So there's nothing efficient. There's no pulley and nothing efficient in your system. And we see quite a few people relying on this as their mechanical advantage system, which is kind of bad here. Let me go over here and get this calculator back out for this next one. So point being is, you will always, if you're not carrying pulleys, you don't think it's important, it is important if you plan on doing this, unless you have like 40 guys ready to get on that haul line and pull. So keep that in mind if you're typically finding yourself using something like an EXO or whatever bailout system and believe that you're going to create it using no other pulleys or roll clips or anything like that. So interesting thing. Here's a 5-to-1. So we're going to look at the 5-to-1s. These are the same 5-to-1s we talked about when we were looking at counting tensions. Now what we're going to look at is what they mean for efficiency. And what you'll see is a 5-to-1 is not a 5-to-1. So depending on the amount of kit that you have, how much you're wanting to carry with you, what your organic assets are, how many people at any given time are going to be on your haul team versus holding security or anything like that in an operational environment. We'll look at what's done typically as a 5-to-1 simple. So these are very common in the fire service, USAR, things like this. We even have a version of that we use with the ARS pulleys. It's really easy to utilize without having to take the step off the deep end saying, hey, I'm going to carry a double pulley, which no one really wants to do in an operational context unless you can do multiple things with it. So we're showing a double pulley here. We split them out just like we did with the tension, so you can see where it goes in, because each one of those sheaves you're going to lose on a double pulley, just as you would if you had two stacked single pulleys on that. So on a 5-to-1, we come in and you can kind of follow around with this. I'll kind of enlarge this a little bit so we can kind of see what's going on here. That one comes into a very efficient pulley and loses basically 10% to friction. So it's a 90% efficiency pulley. One comes in, 0.9 comes out. As this rolls up to our next highly efficient pulley, we have 0.9 coming in, 0.81 coming out. Coming down to the other sheave of our double pulley, 0.81 comes in, 0.73 comes out. So each one of those, we're just going times 0.9, times 0.9, times 0.9. As we're coming up here to an efficient progressive capture. So 0.73 comes in, and then we have 0.66 come out. Now, because of this double pulley, right, things are stacked, right? So we have 1.9 on one of them, 1.539 on the other. We add those together. So on this prusik, which is nothing but a big plus sign, we have sitting 3.44 tensions. So as that 0.66 comes down, we add that to what's sitting right here on our prusik. And so for our typical 5-to-1 simple, which means all the pulleys are moving in the same direction at the same speed, we have a 4-to-1. So your 5-to-1 simple, in the best case scenario, high efficiency pulleys, you're looking at a 4-to-1. And the reason for that is each time that you have it go through a pulley, you're losing 10% of whatever number you're inputting to friction. So let's roll over here to a 5-to-1 complex. So right off the bat, we're going to see one comes in, right? Our direction of pull is different, so we're always going to have more weight on our anchor on this. One comes in, times that by 0.9, we have 0.9 come out. So as this comes in, we have 1 on one side, 0.9 on the other, so that equals 1.9 right here. 0.9 comes down, goes through an efficient pulley. 0.9 times 0.9 is 0.81. So 0.9 plus 0.81 equals 1.71, which is sitting on our first prusik. 0.81 comes up, meets another prusik. That prusik is already holding 1.9 from this end of the pulley. So we add 0.81 to 1.9 and we get 2.71. As 2.71 comes in, 2.44 comes out, efficient pulleys, right? So that 2.44 travels down towards our load. It meets another prusik, which is holding 1.71. So it's 2.44 plus 1.71, which is going to give us a 4.15. Estimated, it's like 1.58 or whatever. So we rounded that up to a 4.2. So real quick, just talking shop here, just us girls. When we look at this, we notice that a 5-to-1 complex is slightly more efficient than a 5-to-1 simple. So we're never at a 5-to-1, right? Our goal is to reduce friction as much as we can, so our actual mechanical advantage, once we have friction into the system, gets as close to our theoretical, that 5-to-1, which we're never going to reach, right, until we get 100% efficient pulleys and we're not dealing with gravity and all this other shit. So as we do that, the more efficient we can make our system, the closer that number is going to get there. So when we look and compare these two, we notice, okay, this one's equal to about a 4.2 to 1 on a complex. Our simple is about a 4.1. Why would the complex be more efficient than our simple? And when we look at that, it's basically because it has one less pulley. So to build a 5-to-1 complex, I just need to build my 3-to-1, which has a pulley up here, or a progressive capture, a micro traction, Spock, whatever you're using up here that's efficient. A high efficiency pulley here, high efficiency. So I just have 3 pulleys in that system. If I come over here, I'm looking at a double pulley, which is 2, 3, 4. So that's my change of direction into there. So I have 4 pulleys. So the added efficiency on a 5-to-1 complex is just because you use one less pulley. Because you use one less pulley, you did not input another 10% of friction into your system as you did with your simple system. Now with that complex, you have multiple resets. So we're not talking about efficiency of operational use. We're just talking efficiency of utilization of force in it. Now we're going to come over here to a 5-to-1 crevasse, which is one of the ones we talked about in counting tensions also. This red line over here represents a quarterlet. It's a different line. So a lot of times you'll see in mountaineering that actually being quarterlet. And in a case like this, what you have here is you have what looks to be a 3-to-1 on the yellow system, right? But this doesn't hook in directly to the prusik. This actually hooks into a second line, which is anchored here. So if you're looking at it, this is looking, very much like a 2-to-1, which is then being pulled onto the system. It's complex, so we have to count tensions in this. Some people are gonna make mistakes thinking it's a 3-to-1 onto a 2-to-1, which it is not. So when we look at this, we count the tensions, we know it's a 5-to-1 crevasse. But when we look at the weight distribution coming through here, we have to be handled a little bit different because we have two different systems in here. So the red is one system, the yellow is the second system. So as one comes out, 0.9 comes out of this pulley. That leaves us at 1.9 at the head of this pulley, which happens to be what's being pulled on by the system here. So when we look at it, we need to continue on where we're at. So with one coming in, 0.9 comes out. So we have 1.9 here, which is being pulled. So if 1.9 is right here, 1.9 comes in, we times that by 0.9, 1.71 comes out and terminates up here at the anchor. So now we can come back up here. So now that we know what we have is we add those, and that's what equals the prusik is 1.9 plus 1.71 equals 3.61, which is sitting right here on that prusik. Back to the top. So we knew that 1 came in and 0.9 came out. We already worked this part of the equation. 0.9 comes up. 0.9 comes up to an efficient pulley times 0.9. We have 0.81 come out. So as that 0.81 comes down, it meets the prusik, which is attached to the yellow rope, which is holding 3.61 tensions. We add those together. So we get the 0.81 plus the 3.61, which gives us a 4.4. Basically, it's a 4.4 to 1. So that is actually the most efficient of these systems. Not necessarily for operational use, right? I don't want to be carrying extra cordelettes, setting up a bunch of crap and doing all this other stuff. Point being is, why is that actually more efficient than either of the other two? Because when you're looking at it, kind of have the same amount of pulleys here. So I have 1, 2, 3. I had 1, 2, 3 here, yet this one on my right is more efficient. And it is because this one has the rope moving through this, the rope is moving, a single rope is moving through all these pulleys. It's all part of the same system. So it's constantly being degraded through each of the pulls. So after this number gets reduced, so 0.9 coming out is 0.81, coming up, meeting up here, and this number is constantly being reduced because of the friction. Because I have two systems, it distributes it out and it never goes down as far as if it was just one single rope going through this. So when you look at this, this just stayed very, very efficient with 1.9 coming in, 1.71 coming out. So when you put those numbers together, it's pretty high. This one, you know, you only lose it through one, and then the second, it's not that the yellow line's not going through this other one. So when we're looking at it, because you divided that into two systems, it just maintained a higher efficiency of a 4.4 to 1. So just kind of getting your brain wrapped around that. We'll move on. So this is interesting. This kind of goes against what we were learning back in Tech Rescue years ago, is if I have just this kit and I have to build a system and I've got inefficient things in it, like maybe not even a pulley, but I've got to go from a 3 to 1 to a 5 to 1. Using the same kit, where does the pulley go? And here it's pretty easy to see. We want to put that pulley, the most efficient pulley we have, we want to put that wherever our hands are grabbing on the line to haul. Whatever pulley is right there where your hands are is where you're going to want to put the most efficient pulley. The reason for that is like high octane gas, right? We want to put efficiency immediately into that system. Back in the day, that wasn't the case, right? People probably remember being taught different things of where that efficiency goes, because they were looking at the system in the opposite direction of where you're inputting force from. Our input comes from the backside of that, right? That's the 5 to 1. So we are that 1. We want to magnify that as close to 5 as we can. So we want that pulley as close to where our hands go at all. So in this case, right, we had a 3 to 1, and then we're like, gosh, shit, let's do a change of direction because this is kind of hard to pull. Let's just build a 5 to 1 complex. I don't have another pulley. Slap a carabiner on and let's make it happen. If you see what happens on this, as soon as that 1 comes up, it automatically just starts killing your efficiency. So right off the bat, instead of 1 coming in and 0.9 coming out like I have over here, 1 comes in, 0.45 comes out. So I've just dropped it significantly. And then from there, it just dumps and I never gain that efficiency back. What I want to do is input good stuff and let it kind of slowly degrade through there, which is the case that we did here. So when we look at this, I have a 2.5 to 1 on this system, where when I build it into this 3.41 system, you'll see what happens is I'm able to input 1 here, 0.9 comes out. Now is where it kind of gets killed. So, right, so 0.9 comes in, 0.405 comes out. As I'm coming up here, I have 1.9 sitting on this prusik right here. So 0.405 plus 1.9 equals 2.301, comes in, 0.21 comes out because I got efficiency there, my progressive capture. That 2.1 comes down, meets with my 1.305, I got a 3.4. So just changing the position, same kit, just changing the position between my carabiner and my pulley changes me from roughly a 2.5 to 1 to a 3.4 to 1. So what that means in real-time force, if I'm lifting a 300-pound load, that means on the inefficient system where I have the carabiner next to my haul lines, I'm looking at 120 pounds of force to input to get that moving. On the position where I have a higher efficient pulley, that goes down from 120 to about 88 pounds of input force that I have to do just by changing the position of where the pulley is in the system. So garbage in, garbage out, try and make it so it's halfway decent in and maintains somewhat decent crap out. All right, so as we're in here, this is the last 2 slides. So just to grasp the goofiness of things and why you just need to train on your crap, never make assumptions that you know more than you do. Right, we're all just students of the game, or else as soon as we think we're a subject matter expert, we're gonna look like a moron. So playing around with some stuff, a couple things came out of this that really represent the non-linearity of our systems. So at no point can we say, hey, this is a given because this is more efficient. Even if I did equal swaps out of shit, it's going to maintain that efficiency. And you'll see, based on different systems and how you build them, it doesn't come to fruition. So what I want to look at is the 5-to-1s, totally efficient, comparing the totally efficient ones to adding an inefficient progressive capturing. And we'll see what it is. So our assumptions on this one, and originally when we saw this, it was done with utilizing like a Petzl ID in there. And I just put a Grigri in there. So we're going to change the efficiency of what we said the Grigri was, just for the take-home point of this, of what basically the efficiency of the ID was with 11 mil, but we're using small mil. So our Grigri is going to represent 25% efficiency. Our Edelrid Spock, which is uber efficient, is going to represent 90% efficiency. So let's just look at this one for a second, right? This is a 5-to-1 simple, very efficient. Everything on here is very efficient. We've got the ARS magnet pulleys, which starts off as a double pulley, but you can actually separate them and do 2 single pulleys with them. Phenomenal piece of kit. But when we look at this, everything in our system is efficient. And so as we do our 5-to-1, we come out with what it truly is, pretty efficient, a 4.1-to-1 mechanical advantage. When we look at our 5-to-1 complex, as we saw on the previous slide, everything is efficient in here. We know that it's slightly more efficient than a 5-to-1 simple because it utilizes 1 less pulley in the system. So that's shown right here, where we get a 4.2-to-1. So right off the bat, if we say, okay, here's my 2 systems, for whatever reason, I'm going to just use the 5-to-1 complex because I know I can get away with using less pulleys. That means less crap I got to carry when we're doing a bunch of other tasks. Whether you're hiking in far, you're doing whatever, or just having the mechanical advantage, it's just a contingency plan if something goes wrong. I don't want to have to carry any extra ounces of anything on me. So that being said, a linear solution to the problem I'll give you here is, oh God, because it's more efficient than a 5-to-1 here, or a 5-to-1 complex is more efficient than the 5-to-1 simple in this situation, regardless of what I change, if I change the same thing in both those systems, the 5-to-1 complex will always be more efficient because it still utilizes less pulleys. And that is not true. And this kind of bothered me for a little bit. And there's a bunch of theoretical reasons why this will work out. But I think the reason that we'll show you is the main reason, and it'll make sense, maybe. So if we're looking at this, I replaced the Grigri into the progressive capture spot of the 5-to-1 simple and of the 5-to-1 complex. All things being said, common sense would tell you, listen, the 5-to-1 complex is already slightly more efficient. Just adding the same inefficient device into both systems, the 5-to-1 will still be slightly more efficient. And as we look at this, we will see that is not the case at all. So if I put the Grigri in here, everything's efficient. It's moving through my simple system, comes up to here, into the inefficient progressive capture, and comes down. What I end up with when you work these numbers out is about a 3.6-to-1 mechanical advantage, which isn't crazy crappy, right? But you'll see that there's the 3.6. So I get a 3.6-to-1 over here. So we assume we'll probably be a 3.6 or above on the efficiency of a 5-to-1 complex because it still does have less pulleys. But when we work that thing out, it dramatically drops into the toilet. So you start theorizing. So think about why that would happen. Why would my efficiency go to crap on my 5-to-1 complex just by adding the same device I'm putting into that simple, right? So just by adding an inefficient progressive capture into my 5-to-1 complex, it just took just a dump in my system. Yet over here on my simple, which was a little bit less efficient originally, but now it smokes it. And now it just smokes my 5-to-1. So why would that actually happen? So, you can start theorizing, going, okay, listen, you actually have 2 anchors over here. So maybe it displaces the weight differently in there, but we actually can't quantify that, right? We really can't quantify that when we're looking at that. It probably maybe plays a role. the other side that I was looking at originally was, well, you're pulling directly out of an inefficiency thing over here on the 5-to-1 complex. So that's got to be part of it. It's a little bit of it, but it's not the whole story. So when we're looking at this, all things being created before we end the slide is take a guess on what you're going to come up with. So, right, 5-to-1 simple versus a 5-to-1 complex. When everything's efficient, 5-to-1 complex, slightly more efficient because it has less pulleys. I make the exact same switch, putting a gree into the progressive capture position of this. And not only does the 5-to-1 simple stay more efficient, this 5-to-1 complex literally just jumps into the toilet, like exponentially jumps into the toilet. So why is that? First, I'm going to remind you before we go back, because this plays a role in it. Remember when we were looking at the slide that talks about, okay, you have the same, I'm probably around here somewhere. There we go. If we are trying to figure out where we want to place a pulley with all things being equal, where does this pulley go? It goes closest to our hands, right? That's what's inputting efficiency into our system. And you can see the difference it makes, right? From a 3.4 to 2.5. It makes a big difference because I'm inputting efficiency into my system. So remember that, because when we look at these systems, these are not the same, right? What we got to remember is on a 5-to-1, 5-to-1 is a simple mechanical advantage because all the pulleys are moving in the same direction at the same speed. So it's a simple thing. When we get into a complex or compound, right, we have a mechanical advantage hauling on a mechanical advantage. So just to put that into a little bit of perspective, let's go ADHD off topic for a second and look at a compound, right? It's a typical compound. Remember, on this, I can see that it's a 9-to-1, right? I can count tensions and do all this other crap or whatever, or I can just look at it and say, okay, there's a 3-to-1 right here being hauled on by another 3-to-1. So I have got a 3-to-1 attached to the haul line of my first mechanical advantage. So I have 2 mechanical advantages on here. What's called a front mechanical advantage and a rear mechanical advantage. So this 3-to-1 is our rear. Our front mechanical advantage is right here. So it is attached to the haul line of a 3-to-1 being hauled by a 3-to-1. So what do we do in those cases? We multiply them, right? That is the multiplicative non-linearity of a compound mechanical advantage. It is no longer additive like it is in a simple mechanical advantage. So having efficiency, think about this. This point right here is really critical to have something efficient in. Why? Because just like that previous one where we said, hey, here's the same kit, where does the pulley go? Where does the carabiner go? It goes closest to your hands. We want it efficient here because I'm inputting it because this is where my hands are. But the hands of my other mechanical advantage are on the haul line of my first mechanical advantage. So this needs to be efficient. So we look at a couple numbers here, then, and I'll kind of zoom this in a little bit, is to show the difference. Alien head here. If this was an efficient pulley, then when this 2.7 comes in, 2.43 comes out. So I maintain great efficiency, and it's magnified. If I would replace that with a carabiner, which is approximately 45% efficient. So if 2.7 comes in, I times that by 0.45, I've got 1.22 comes out. So it destroyed it fast, right? Big difference between these numbers, especially when you're looking at pounds of force that you're going to have to apply. But, big but, let's say just for the sake of argument, not that I've ever put a freaking gree here, but just so you can see the effect that something that is 0.25, right, 25% efficient has in your system, is if that 2.7 came in to something that's 25% efficient, 0.68 is going to come out. So you get literally treated like you're in a prison cell in somewhere in Mexico. Like your system just got completely annihilated. So that is an exponent, right? That is multiplicative because these systems are multiplied together. So keeping that efficiency, especially at critical points, is huge. So let's go back to our original ship. So when we're looking over here, I have a complex system. So a complex system is an MA pulling on an MA, but it's neither simple nor is it compound. That's how it gets classified as a complex. In this case, and one thing too, on that compound, remember, whenever you have an MA pulling on an MA, your pulleys move at different rates. So this back MA system that we put onto the 3-to-1, that second 3-to-1 what we put on there, when you're pulling that on your 9-to-1, that back system is going to move 3 times as fast. So you're going to constantly be, if you're using the same anchor point, you're going to be resetting that back MA way more times throughout your entire system, depending on what your throw is. But you're going to be resetting that a lot more than your front MA. So when you're looking at that, if this is my front pulley and my other one, this is my second MA, you're pulling this thing, and it's just pulling it way faster, right? Because it's more inefficient, right? You're pulling on a 9-to-1. So you're pulling 9 feet to move this 1 foot. Here, it's still moving on a 3-to-1. So you're having to do multiple resets. So the big thing on this is if you have pulleys that are moving at different speeds in your system, right, you've got a compound or complex problem. And wherever those two meet is multiplicative, right? So when we look at this, here's my 5-to-1. I am pulling down. Not only am I pulling down, but as this is, it's complex, my pulleys are collapsing. This upper pulley that's up here on my 5-to-1 collapses way faster than this bottom one. So with that, that's why you have to do so many more resets on that back one on your 5-to-1 complex. It's pulling at different speeds, which means it's pulling on another mechanical advantage. So the point to remember is because it's doing that, whatever it's pulling against needs to be efficient, or not only are you going to lose efficiency, you're going to lose efficiency on a magnitude. And that magnitude is a multiplicative, which is why over here we can multiply these things together. So that is kind of what happens. So what I wanted to do is show you, here's the original one again. So 1 comes in, 9.9 comes out, blah, blah, blah. We go through the whole system. All of a sudden, 2.71 goes in, and we just get completely screwed with a big number going in and 0.68 coming out. I mean, like terrible. So that 0.68 comes down to the 1.71, and that's where we get a 2.4-to-1 on this 5-to-1 complex with a crappy ass progressive capture. So just screw it around. I said, okay, let's just to prove the point of what's going on here, let's change out. So same kit, let's just move shit around. So on this, I kept the high efficiency pulley here. I moved the gree down here. Not that I would ever even consider doing some moronic move like that, but just so we can see the numbers and how the numbers play out. So everything is apples to apples on this one. Just to see it, let's just move the gree down here, and we're gonna take this pulley that was here, and we're gonna move that up. So now same kit, just different positions. So now as I input this thing, you're gonna see when this is pulling down, and it's a high efficiency pulley, although it's 2.13, because I lost some shit down here, it's going into the point where it's magnified. It's multiplied. And so this 2.31 that comes in still comes out with a 1.9, right? Which isn't too bad compared to coming in with a 2.71 and coming out with a 0.68. So that 1.9 rides on down, hits up with my 1.13 that's over here. And I actually, just by changing shit around in my system, went from a 2.4 to a 3.1, which I'm happy with, right? That's not completely crappy. So what is retarded is that we kept that in, right? That's not something we're going to do, but just to compare it, we did. So in that system, if this is what we're given, the most efficient way to play that thing out is just to ditch the gree and use a carabiner down here, because the carabiner still is more efficient than your descent device, man. So on it, having a pulley up here, when we worked this problem out, where I took the gree completely out, all I did was kept the carabiner that the gree was attached to, plugged that onto my rope. Now, when we work that system coming out, I actually jump it up to a 3.4-to-1. So when we look back at the comparisons before on the 5-to-1 simple, I had a 3.6-to-1. So still not as good as that is, but considering what I'm working with in a complex system with an MA pulling on an MA, and I'm given a crap sandwich of having something very inefficient, coming up with a 3.4-to-1 isn't too bad. So when you look at it, start messing with your systems, because they're unpredictable sometimes until you actually put pen to paper and then put a weight on and measure what the hell you're doing. It makes a big difference, especially if you're using small party rescue type of techniques where I'm carrying minimal equipment, we're moving very quickly, regardless of whether that's operational and SOCOM, or you're in a mountain rescue team, or you're in a quick reaction force doing something in the fire department with USAR as a QRF. So know the equipment you carry, know how to build systems, know how to exploit systems, and realize that you're gonna have to play around with it, tinker around with it quite a bit. put loads onto it, and see where you go from there. So in the end, always err on the side of efficiency, and really probably violence will help too. And exploit whatever you can. Just tinker with that shit as much as you can and see what you come up with. And you'll probably be surprised in some of those areas. First things first, when you do that though, you'll have to get somewhat of a 1-to-1 type of ratio to be able to see how efficient some of your stuff is. Now, if you're looking at pulleys, if you have a sealed bearing pulley, that's usually looking somewhere into that 90% range, plus or minus whatever. Once you get into your bushings, which you still see in a lot of tech rescue bags, you're literally lowered your pulley efficiency, which is a pulley, but it's a bushing. You're down into maybe a 70, 71, 72% efficient system. It also is dependent on the rope that you're using. So we'll get into probably when we talk about the ways to do different piggyback systems in the next one. We'll add on how the rope bending and things like that change your efficiency with what you're doing. And it's really very specific to what you're using, what diameter you're using. There's times where you can go down in diameter, keeping the pulley the same. So if you look at the pulleys that we use a lot of times, those are typically considered mini pulleys that can go up to an 11, but they're 1.1 inch usually. If we take that down and we use a 7.5, we get a higher efficiency in it than if we had an 11 in it. If we go down to the 6 mils that we use, right, which are specific to what we use, we gain even a higher efficiency than we do off of 7.5. So a lot of things make differences on that, along with the weight and what the construction type is of your pulley. So you're gonna have to play around with it, and you could get kind of amazed and start building like a lot more efficient systems, right? Because this is a craft, and that's what you do. So that is it for this one. This is it for the counting efficiencies and discussing a little bit of nonlinear behavior. The next one up is we're going to show some voodoo piggyback systems that you can do, whether you make your own piggyback system, your own set of fours, or you're using something like the Aztec, or what we use, the individual MA from NAR is uber efficient. So we're going to show you a bunch of different ways that you can take what typically people look at as just a 4-to-1, swip it around. It could be a 5-to-1, depending on which orientation you put it on, and show you how right off the bat, without even really adding any other equipment carrying, how you can turn that into a 9-to-1 capability using different pulleys in that thing. We can actually take a set of 4s and take it down to a 3-to-1. So we can do a 3-to-1, a 4-to-1, a 5-to-1, a 9-to-1. And then by adding just a little bit here and there, we can build that thing up to, like a 23-to-1 without losing a ton of friction in our systems. And it'll just give you more options on crap to do if you find yourself by yourself having to haul something stupid heavy, or getting into like vehicle recovery or certain things with moving stuff in confined space. So that's it. Send us any questions that you have, and also hit us up any topics that you want to hit on any of these screencasts.
The crew is back. I be climbing team like Super Cat. Making riggers, rock that friction, what you think of that? We fear no one, oh no, here they come. That Element Clan, road rescue shogun. Dropping 200, Kern Mantle, down like what? And rocking killer beats to the eardrum. Click your beaters, tip your hats. I got ice water blowing up both my calves. Sand blowing down as I hit the crevasse. Don't bother me, man, I got another pass.